All right, recording. So yeah, so we're on to the fourth lesson here. So we've the last three we started out, we made the, let's go back to the home page here. Remember the first lesson we just did the kind of the outermost layer of the onion, tried to get the payload and the command for a message. And then in the second lesson, we learned how to get kind of the inner layers of the onion for a version message. And so we could read a version message. And then in the last one, we did kind of everything else to finish the handshake. We learned to serialize, to write these messages, and also how to do the VARAC. And then at the very end, if you want to pull this up, we wrote a really shitty little program that could connect. Is a simple crawler. So it would just take a couple addresses, and it would just kind of pop from them, just to basically use them as a queue, just grab the first address and do a handshake, and then it would just listen and try to get an adder message. If we look at our handy, I think we can just, we can do it like, we can just get it here. Yeah, so the adder message here in the protocol docs is the message where you tell your peers what addresses you know about. So we haven't dealt with this yet, and I just included, last time I just included a kind of a little implementation of this class. So all it is just a varint, and then a list of these addresses, net adder, just like we dealt with in the version message. Mostly just the IP and the port is the important part. And so once we just listen for these, and we try to wait until we get a list of them. And if we do, then we can kind of continue crawling. If every one of our peers gives us kind of on average more than one address, then we can actually go and crawl the entire network, as long as we keep getting kind of unique addresses. And so that's what this did, and we ran it a little bit, and we saw how slow it was, right? If you remember it, like it took forever, and it didn't really get very far. And so we're going to kind of continue on this idea of crawling the network. And I think it's a cool, it's a good little project to do here at this stage, because we only need to basically know how to parse, or how to deal with three types of message, right? The version message, the VARAC message, right? The version message, VARAC message, and adder. I mean, it's no accident these are the first three. Like, these are kind of the first three you deal with. Version and VARAC is like, can I connect to the network? And then adder is like, okay, I've connected to the network, but just in case my peer goes down, like if they just turn their computer off or something, I want to stay connected to the network. So I need to get more addresses and more peers, just so I can stay up if I lose my peers, right? And so this little project is cool, because we only really need these three messages, and we can kind of go get a sense of how the Bitcoin network works, how you can just connect to anybody, and how everyone's interconnected, and how you don't need an API key to talk to them. Like, this is my favorite part about this sort of a program, is because, if you're doing normal development in anything regarding finance, like anything interesting, you need an API key. You need some sort of sign a contract to get access. And Bitcoin's so amazing because we can just write this like little program. No one gave us permission to do this, and we can talk to everybody. The entire network will return our call, which is so different from anything else in the finance industry. So, and secondly, like, we saw how slow this is, right? And we're going to run a slightly modified version of it here. And what we're going to basically do is we're going to do some profiling. We're going to try to figure out why our code is slow. And here's some graphs, about how our code is being executed. And we're going to try to figure out why our code is slow and how to make it fast. So we want to be able to crawl the whole Bitcoin network in, like, let's say an hour, 10 minutes or something. I don't really know what the fastest we can get it is, but if we can kind of crawl the whole network in a short amount of time, that'd be really cool. And then we could have a database full of all the data we get from our peers, and we could kind of learn about the network a little bit. So that's what this lesson is going to be about. So anybody kind of have any questions about that before we get started?
So by crawl the network, do you just mean establish connections or receive information from all those peers?
Yeah, yeah. So I mean, like crawl, you know, like the best example of a crawler is like Google, right? Where, you know, it'll go visit a page, and then the crawler will go and read all the HTML, right? And it'll look for A tags or something, right? It links to other pages, right? And so it tries to build a graph of how every link on the internet is connected, right? And then it does some other things like assign weights to the various links and figure out what sites are the most important. So, you know, and so that's basically what we're doing here. We're going to visit peers, and then we're going to try to see who they're connected to, right? And then we'll connect to them, and then we'll see who they're connected to. And we're just going to keep going until we start, basically we don't find out about any new peers really. We kind of visit everybody. And so that's what I mean by crawl.
So understand the network topology. It's a bit different to like Google crawling, isn't it? Because that actually that's collecting information on all of those different links.
Rather than just we're going to save their version message.
Yeah. Okay.
One of them has a little different version message, and if we want to, we could we'll save their IP or their port. We could probably try to somehow get a little information about where they're geographically located. We could do, we could try to figure out if they're running in AWS or not, stuff like that. So we could do kind of a lot. I mean, the inspiration of this is this BitNodes thing that we dealt with earlier, right? Like that's what this does. That's how they find all these nodes, is they have a crawler that's running constantly. And it's written in Python, which is kind of cool. So we're just going to build a mini one of these. You can go and figure, so here they're saving the version message, right? Node network, node bloom, node witness. These are things we dealt with earlier. What their IP port is. So yeah, this is our crawler's just going to do this. That makes sense?
Yep. Thank you.
And it's important too, because if we want to do our goal here is to get to the point where we can do initial block download, and it's a good project, because if you can do initial block download, you really understand how Bitcoin works, right? Like that's the heart of don't trust verify, right? Is being able to do initial block download is if you can start from the Satoshi's first transaction. And I mean, we won't be perfect. Like we won't be able to catch every corner case, because that would just take forever. But we're going to get the gist of it. We're going to be able to basically figure out what the state of the entire UTXO set is, and who has how many Bitcoins. And that's really that's the heart of Bitcoin, is that's what that's what owning Bitcoin means. So yeah,
with Bitcoin Core, you don't establish an understanding of the topology of the whole network, do you? You just connect to a few nodes, and then
exactly.
if they aren't able to provide the information you need, then you might connect to more.
Yep. And so the reason, exactly. So this is not strictly speaking necessary, but I think it's a cool project because what we're going to need to do the initial block download is we're going to need our program to be fast. And so I'm going to teach you some basically one technique for making a networking heavy program fast, a program that spends a lot of time waiting for your peer to send you messages. If you do like we were doing here initially, where you only have kind of, if you do the way we're going to start, it just takes forever. Like this version, it's you get a new adder message once a minute basically, and so it takes forever. And so we're going to speed this up, and then that's going to help, because when we do initial block download, we'll already basically know that technique, and we'll be able to do it for initial block download as well. Because we're going to have to, with initial block download, you want to contact 8 peers or 16 peers or something at the same time. And you need to, this program talks to one at a time. And so it's going to be super slow. So we want to figure out a way to talk to many at the same time. So this is an excuse to start thinking about speed and have one technique, so that once we get to the initial block download, we'll already be a little familiar with it.
Cool. Sounds good.
And it's also, it's like a simpler, like I don't want to jump right into the initial block download because it's like, it's a hairy beast, you know, it's, it could get out of hand fast. So yeah, this lesson's like sort of a little bit more bare bones, but so let's just start from the top. So it's the same thing we did last time. This just like loads this little auto reload widget. So this is mostly helpful if you like change code that we're importing, like any of this stuff. You don't have to restart the notebook to reload the code. And so this is mostly helpful for me when I'm editing this stuff. But then we also import this counter, which is we'll use later. Oops. So yeah, we execute that, and so let's just look over this really ugly. I'm sorry, this is so ugly and terrible, but it's a really shitty piece of code here. And so the simple crawler added a couple things. So last time we only had one address. This time I'm going to give you 5 addresses just to, in case there's an error with one of them, our crawler can keep crawling. We'll give it a little bit of a head start. And then we'll have this, actually we don't need this. So same thing, while addresses, the first thing we're going to do, we're going to record the start of the for loop. It's just a time.time is just like this. We've dealt with this before, but it's Unix time. It's like the number of seconds since 1971 or something. It's like this is just how time works on a Unix computer. And so, you know, if we call it, just to give you a little understanding of what this does. So we're going to call it time.time. Oh, we got to print, sorry. So if you can see the first one, it ends in 5.0, and then we sleep for a second. And then this one ends in 5.1. So you can tell it's just incrementing. Like it's almost the exact same number, but it's 1 bigger after we sleep for 1. So you can see that it's just like increments every second. And so this is how we're going to keep track of how long each loop in our code takes, so that we can understand a little bit of, you know, how quickly it's moving. So that's what we do. And here we just we get a new address, and then we do the handshake. And this has a try except loop. So I don't know what did that. Okay, we'll reload. I don't know why it's doing this. Okay, sorry about that. So the try except loop is basically like, try except is when you're going to run something that could have an error, and you don't want the error to crash your program. You know, in Python, errors a lot of times are just to communicate. They don't mean that like your program failed. It just means like a little part of your code failed, and then basically a portion of code above it should watch for the failure and handle it. And so what we're going to do is we're just going to, if we get an error, we're just going to print it out, and then we're going to, we have this runs variable. This is just going to be every time we have a run of our for loop. When it ends, we're gonna stick a couple pieces of information on there, like when it started, when it ended. Wait, what the hell? Just a second. Interesting. Okay, I thought we had a little, just a second. I thought we had one extra thing in here. Okay, I screwed up somewhere. Well, do we need that? We don't actually need that, I don't think. Well, we'll just continue. There's something weird with my Jupyter Notebook. It just like reloaded and deleted some code. So sorry about that. But so what we do is every time so if we catch an exception here, we're just going to stop the for loop. Continue just says like go to the next loop in your for loop, right? And so if the handshake fails, we're going to append a kind of a little tuple onto this runs array that just says when it started, when it stopped, and what the result was. Failure is just like it failed, sorry. And then we're going to go to the next loop, right? If we don't get an error, we're going to keep going. And we just set this Boolean listening. And this just is another, like an inner for loop it's going to take our socket that had a handshake, and it's just going to try to read more packets on it, and then we're going to do something in case those are adder messages. And so any questions there? I'll go into this part of the code more, but any questions on this sort of top part?
Not from me.
Okay, cool. So we're going to do the same thing, try except loop. We're going to try to read a packet. And I just have this one type of error. This is basically an error when they stop talking to us. That it's a bit of a hack at the moment, but this is like one error that our code currently can't recover from. And so if that happens, I'm going to print it out just so you can see it in the console. And do the same thing. We're just going to append the basically a snapshot or like a record of what happened in this for loop. And then this one's going to do break. So break means like end this inner for loop. So this is kind of confusing, and I apologize for that. But break will just leave this for loop. And then since we're at the end of this for loop, or this while loop, it'll just go to the next address. So that's what this does. It just goes to the next address. But if we don't encounter any errors, eventually we'll get one of these adder commands. And all we do there is we just say, hey, if it contains one address, and if that address is the same address that we're already talking to, let's ignore it. Because I don't know why, but sometimes they'll send you, your peer will send you their address, which is like stupid because you already know their address because you're talking to them. So that happens a lot, and I don't know why they do it, but we're going to ignore those. And so here's the money shot here is like, okay, otherwise, if there are addresses we don't know about, let's just take our addresses array, right, the thing we defined up here, and let's just add a couple more things to it. Let's add this this tuple, just like, IP port. And sorry, some of these variables are kind of confusing. Like I need to simplify this so it's a little easier to read. But all this does is it adds some new ports to our list. And then it says, okay, we succeeded. This state is success instead of failure. And here's the start and the end times. And let's do listening as false. So, and actually, let's just do this. We could get rid of listening. If we just say while true, and then here we just say break. You don't need to copy this. Yeah, that's a little simpler. So this will just exit. So we have the same little crawler, but now we'll be able to kind of we've instrumented it a little bit. We have a little list of the different runs it makes. So if you let's see here. Yeah, so I guess I don't run it here, but so if you look at this next thing, so any questions about that? Any questions about the rest of this code?
Yeah. On the second while loop.
Yeah.
What does packet equals packet dot from underscore socket actually do, like mechanically?
So packet dot from, that's a good question. Let's see. I'm just sharing one screen here, so I think I can show it to you this way. So if we go and visit, so this is the file it imports from. And this is it's a great question you ask, because this is going to be the thing that this is like the star of this lesson. Like trying to understand exactly what this does is going to be the star. It's going to be the most important part of this lesson. And so what it does is it just calls these little read X, read magic, read command, read length, read checksum. It calls every one of these, and at the end it basically, like what this does. So it's a class method. This is just, you don't have to, for the purposes of this lesson, class method is just a way to kind of call to create an instance from for a class if you don't kind of have the command and payload handy, right? Like at this point in our code, we don't have a command or payload. We just have this socket, and a peer is going to send us bytes over the socket, and inside those bytes are the command and the payload, right? So this is just a way, packet.fromSocket is just a way to pass a different type of object, in our case a socket, which is like really a weird object, right? You just read bytes out of it that magically appear over the internet. So it'll go and read the different types of things, the magic, the command. So this is the lesson 1, the length and the payload length. So command and the payload length are the 2 important ones. And at the end, it creates an instance of itself, which is packet. It creates a packet instance with this command and payload. Does that make sense?
Yeah.
So what it's reading? So what it's reading here, let me finish this. What it's reading is, we should actually go and look at one of these. So read magic. It's just reading right out of the socket. Like socket.receive is actually like a C. This just directly calls C code, basically. Like socket.receive is something that's implemented in your, do you have a Unix, like a Mac or a Linux operating system? This is like implemented in your, like, let me think how I can. Like if you go to your terminal and type, if you go to your terminal and type man, M-A-N, space socket, just all lowercase, man space socket, you'll see this big, man is for manual page. This is like, before the internet, this is how you'd look things up. It was like the manual in your computer. So, if you look at this page and search for a receive, R-E-C-V, to search, you just hit the / you'll see a bunch of, you'll see instance of it. Like this is actually a thing your operating system does. So all we're doing is we're just asking the operating system, hey, I got a socket. Could you send me the next 4 bytes in the socket? And if they're not there, just block. Just wait until bytes show up, right? So if your peer on the socket doesn't send you any bytes, this will just sit there forever. It won't. You'll sit right on this line forever, and nothing will happen. Does that make sense?
Yeah.
Okay, so let me just demonstrate that. So I'll just do a little. So we have socket imported. So let's do. Let's do. What do I want? I want connect. Yeah, so let me just give a little demo here. Oops. So sock dot. So this will just connect to one peer, and so this is just going to create a socket, connect to a peer, and then it's going to wait for, it's going to read 4 bytes. And so you see what's happening here? See how over here on the notebook there's a star? That means it's blocked. Like so if we create a cell below it and just do like print 1, see, it doesn't print. Like it's stuck. Does that make sense?
Yeah.
So this is the same thing that packet.from socket's doing. It's just doing this a couple times and creating a packet instance from it. And this is going to be really interesting. Like understanding this is the whole point of this lesson. This is like when you're doing any sort of network programming, your code is constantly going to be doing this. It's just going to be waiting a little bit. And if you don't know how to deal with this, your programs are all going to be super slow because you're just sitting around waiting. Like if you can't deal with this sort of a situation intelligently, your program's never going to be worth a shit. So, so yeah, this is is a good question. This is basically what's happening.
And you're waiting for a response, yeah? That's what you're waiting for.
So,
so why is the node so slow to respond?
Because we haven't sent them a version message.
Oh, okay.
The only way you can introduce yourself to your peer is if you send a version message.
Okay.
So remember when we go back to lesson 1 here.
I remember. Sorry.
Yeah. So no, it's fine. But just to because like you forget these things, you have to kind of remind yourself, right? So remember lesson 1. That's what we did. We connected, and then we waited, and nothing happened, right? We can execute this, right? Like Oh, well, I don't have this stuff filled in, so it won't really work. But here's not so. But similarly, if we do the same thing, but we just send this magical version message, then they'll respond, right? So if we don't send the magical version message, I'm just going to comment this out. See, then we have the star again. We're stuck. And you can hit the I twice to kill it. But if we do send this magical version message, then they respond. So, so yeah, that's just a kind of a little review of what zoom out review of where we're at and kind of what we're doing. So yeah, any more questions about this kind of ugly piece of code?
So I have one more related question. So what is the like universe of stuff that we are consuming when we're getting stuff back?
Yep.
Like what exactly is all that?
This is the universe, message types in the protocol documentation that we've been kind of looking at. There's 27 of them. So these are like, you know, when people are running their full node, the full nodes speak a language, and the language like basically has 27 words. Like there's 27 different things there's like 27 different things you could say, so to speak. These are all of them, right? And we've dealt with 3 of them so far. We've dealt with we've actually only dealt with 2 of them. Version message and var_ack. Those are the only 2 we've actually learned to decode and really understand everything that's contained. But when, you know, when we ran our code last time, like let's just, so I'm going to make a cell below this. Sorry. Below this, and let's run it. So you see what's happening. So the first thing it says, I'm connecting to this peer, right? It's the last one in our list. See, it ends with 112. So because it just gets from the back of the list. So I'm connecting to this. So this means I did connect, and now I'm here. I'm going to wait for trying to get an adder message. And then it says, oh, I got 1 adder. And so then it's going to, what it does is it's going to add this to the list of addresses, right? And so look, this is an IPv6 address. So this is like the new address format that, eventually this will run out of IPs. Like if everybody has like 50 internet connected devices, we'll run out of these. But these you'll basically never run out of. And so look, in our original list, we did not have an IPv6 address. And so now it's trying to connect to one. So like, look, we're already crawling the network. We got a new IP that we didn't know about, and we're already connected to them. Or we tried to, and so this code here actually isn't able to connect to IPv6 addresses. So that's a bug on my part. But here it goes and tries to connect to another one. It got 2 adders, and so kind of here it's going, let's see. Let's try it again with this log equals true. So yeah, here it's just log equals true will print out all the messages. So at the beginning, we're just getting these var_ack messages, right? And this is all to answer Alex's question, like what is the universe of things we're dealing with? Eventually here, or actually, no, we don't want that, sorry. We want, yeah, we'll print the packet. Okay. So yeah, here's a good one. So we connected to this guy, right? And so after we connected, he sent the send headers packet with an empty payload, right? So we can go over here and look for send headers. Here it is, message 22. Like this is, what does this tell us? So this tells, so this is probably an SPV node. It says, I want headers, I don't want full blocks, right? Like this node does not have the entire blockchain. So it wants to only keep track of headers. And so it's probably an SPV node. And so we could look at more of these send compact, ping is just checking if we're awake. And here's an adder message. So this is the class of things we're dealing with. And this is like, and so here's an inventory message. This is the, well, it's a little cut off because my screen's too small. But this is like how block this is how blocks and transactions are propagated across the network. Like this is one of the most important, when you create your block and a Chinese miner figures out about it like 3 seconds later, this inv message is doing all the work. That's the one that goes and announces it all over the network. So this is how the mempool is created, is kept up to date. This is like the heavy lifter, which is pretty cool. So this is, to answer your question, this is a little taste of what the class of things we're dealing with. And we're just trying to pick off these ones. We're trying to ignore inv. We don't care about that right now. We want adder, because we're trying to learn about more addresses and sort of visit a bunch of people. So this is the only one we care about at this point. Does that make sense?
Yeah, I think so. So we basically, when we connect to a full node, we can if we wanted to, we could kind of ingest every type of message that they have. But for now, we're only narrowly focused on adders. So that's what this code is doing.
Yeah.
Right?
So we probably should. It probably would have made a little more sense to, like, maybe next time we should do this, yeah. So like this is lesson 3. I kind of sent some notes to like, I probably should have spent a little bit more time doing that with you guys, because now that you're connected, it would probably be more interesting to go and figure out some things. But I just kind of ran out of time. But yeah, so this is one of the things, like, in order to do, yeah, that would be a good. Maybe I could like give you like a really self-contained homework assignment where like, it's possible to get one of these inventory messages, go and download whatever, it's usually a transaction, go and download whatever the transaction is associated with it. And then you can go look up the transaction in a block explorer and figure out like, oh, look at this. This is just somebody's transaction from 3 seconds ago. Like that's what you'd find out. So that's actually possible. And so I should probably do that in the next version of the class. But the other thing is this inventory message is actually only useful once you've already done initial block download, because, if it's a transaction, like, well, what do you know about, how do you know if the transaction is valid or not? You actually need an entire blockchain. You need an entire blockchain to be able to verify it, right? You can't verify one of these messages without a blockchain, unless you want to trust someone else. In order to avoid trusting someone else, you got to verify your own blockchain. So yeah, for our purpose, this isn't useful yet, but it'll be really cool. If we can get to the point where we can do the entire initial block download, like we'll be able to go and grab these messages and actually look in our kind of database of the entire history of the world and say like, is this valid or not? And do it just like Bitcoin Core. We'll probably have to simplify it a lot, but that's the goal.
How come we were told about SPV client? Did we ask for full nodes or SPVs?
I don't think we. Yeah, I don't know. I mean, so this is the funny thing is like, I mean, the Bitcoin network, like the protocol itself. I mean, it's like everyone's an equal peer, right? Like my script just joined these people. And so, as we're talking and this script is running, our peer probably sent my IP to some of their peers, right? Because that's what happens whenever a new person joins, they go and tell, hey, I got a new peer. And so, like, I'm not an SPV client or a full node. I'm this bullshit Python script, right? And so it's this interesting thing where like the Bitcoin network itself doesn't really have a notion of this like strong distinction. It's more like flexible and granular. It's like, well, what can you do, and so yeah, that's as far as I can tell. I mean, they could be lying to us. They could be saying, maybe they just don't want. Maybe they get their blocks from someone else. They think I'm a slow. Like, who knows? But yeah, we didn't. I don't know if you can just you can't like query for a full node. You just like go and talk to peers and ask them what they can do. And you kind of got to figure out for yourself if they have what you want. Does that make sense?
Yeah, there's not even a way of like the first time you connect to a bunch of nodes, I can see why you wouldn't know what type of node they are. But
Exactly.
I would have thought after you've connected to a few nodes, those nodes would be able to tell you how useful other nodes are. You know what I mean? But it
Yeah,
seems like
they actually don't. Yeah, I mean, I would too, but they actually, and this is one of the cool things about the Bitcoin protocols. It's like it. I mean, the protocol and the money and like the whole idea is it's like you should figure these things out yourself. You know, like don't trust other people. Don't like you got to figure it out yourself, and that's true for like the individual in terms of like how they hold custody their coins or whatever, or you know how they accept payments. Like there's no trusted, you know, you try to avoid trusted third parties in general, and that's true at the code level too. It's like, hey, I'm just going to give you IP addresses. I'm not going to really like you know your node is fully empowered to figure it out yourself.
This just seems inefficient though. Like I don't think this is an element of trust. This is just like, give me better information, like more.
Yeah, but why would you need them to get like their information could be out of date? You know, like maybe the node changed its configuration.
Well, then you can quickly like update the information.
But you have to go and talk to them first. Like if you're going to talk to them at all, why don't you just, you know?
Yeah. Okay.
I don't know. I mean, it's
interesting.
A little slightly philosophical, but yeah, this is why I think this is so interesting. Is like, in my opinion, people really neglect the peer-to-peer aspect of Bitcoin in terms of like explaining it, and like they focus on the blockchain, which is just like a special list. Like it's not that interesting in my opinion. But like this is one of the like this is the reason why like a government is going to have one of the reasons why a government would have a lot of trouble killing Bitcoin is like it's just it's really hard to you'd have to kill all these nodes, and it's just like this anarchic free-for-all. Cool. So Gustavo's a little busy, so let's just keep going. So yeah, look, this is my script has just been running here, and you know, mostly these INV packets, if you look, like that's almost everybody. You can get a sense, like look at how little like this thing's been handling a lot of packets, and almost all INV, but every once in a while we get an adder, and see at the end of the adder we do a new loop. You know, it's like I got the packets, I'm going to connect to someone else. Interesting. So yeah, so I bet if we decoded this, it would be equal to this, I bet. But you can kind of get to see what's going on. But yeah, so then we start all over. And so I'm going to kill this. I'm going to hit I twice and kill it. But we can kind of see what happened if we see that. Look at this runs variable. Like runs is going to, like this is the thing that it's just a little global variable that we append to every time a loop finishes. And so if you look, like here's the start of the first loop, here's the end of the first loop. So if you look, this was 64, this was 82, so it took about 18 seconds. And there was a success, it actually got a version. And so you see, here is failure, here is success, success, failure. And so, let me see. Yeah, so this is kind of gives you a sense of how the program was working, but it's really slow, right? All that explanations I was giving, it only managed to get, what are these, like 12 addresses? Like it didn't actually do that much in that long time. And that's because we're sitting here, we're waiting forever to get these adder messages, right? We're just sitting here and they're giving these inventory messages. And it's kind of weird because if you look, oh, actually we don't do that. Okay, never mind. So there's one thing we'll do later on that we'll be able to get this, just forget what I said there. We'll cover that later. But this gives you kind of a sense of how our little program is running. And so, yeah, here is just some stuff for in case you don't run it. This is what it looks like. We've already seen that. And so, so yeah, like we can. Well, we'll just run this. These are some. Okay, Michael's leaving. That's cool. So these are some. This is like some runs that I did previously, and so we're just going to deal with these so like everyone has the same data. So this just gives us an idea of what's going on. So if we enter this, we see like runs of 3 is gonna check for like the success or the failure, right? So if you look through each one of these runs we did, 5 times we succeeded, 1 time we failed at the handshake, and the other time we failed when we're trying to get the adders. And so this kind of gives you a sense of whether our program's working or not. And so here's another thing. This is going to just calculate the average duration of like how long it takes, like the average time it takes to get a success. And so our program was, I think it was something like, we ran it for like 7 minutes and we got like 5 successes. So on average, it's taking like 90 seconds per time we run to get a success. And obviously that's slow, right? If we estimate how many days it's going to take to complete, it's going to take about 10 days for our program to visit the whole network, right? Because there's 9,000 nodes in the network, and it takes about 88 seconds per node, and divide that by the seconds in a day, and it's going to take about 10 days for our program to finish. So yeah, I'll just kind of stop there. And anybody have any questions about these kind of little back of the envelope calculations about how our program is working?
Can you explain one more time what the failures mean?
Yeah. So if we go to the top, like, so this, I had like, if you saw at the beginning, like my Jupyter Notebook reloaded, and I think it like deleted a little of the code I had. So let me just, let me look. Where is it? How did I have it? Handshake failure, adder failure. Yeah. So this is how it should look. And okay, so when we're doing the handshake, if we get an error that we can't recover from, let's just, all we do is we just we stop the loop. We just basically go to the next loop with continue. But before we do that, we just take this error, this E, it's an error message, and we don't actually do anything with the message itself. Like in the future we could, but we're just gonna append to our runs a start time, a stop time, which is like now, and then we're just gonna stick a little string in there, like basically what was the outcome, right? And so in our program, handshake dash failure means we failed while we were trying to do the handshake. Adder dash failure means we failed while we were trying to get an adder message. And down here, a success, this is when we actually get some non-trivial adders. This is the same thing, right? Start and then stop. This is the current time at when this executes. And success means like we actually got adder messages. So does that make sense?
Yeah, I guess I meant more like what actually causes the handshake to fail and what causes us to not be able to get an adder.
Yeah, so that's a great question. And this is something I'm still kind of like, I'm not a super pro network programmer yet. So in my better version of this, it's kind of hard because they have so many things printed out. But actually, I think the first one failed, didn't it? No, it didn't. Let's see. This is going to be almost impossible to find one. But like sometimes like if the node is offline, it'll like if somebody had a node and they just turned their computer off, you'd get, there's a couple errors you can get. Sometimes if they already have like too many connections, they'll refuse your connection, and it'll be a connection refused error. Sometimes we'll have a bug in our code and we won't be able to parse the message. Even if the message is correct, we'll have a bug in our code that will fail to parse it. And so those are some of the kind of errors we could get. Like if we go back to our where was it? This one. So I think, like for example, this is one of the errors. If we get a checksum for our packet. If we read one of these checksums and it doesn't match the checksum that we compute, then we raise an error saying, hey, sorry, it didn't match. Or if we somehow got a payload that wasn't the length that it was supposed to be, we'll raise an error like, hey, I tried to read 10 bytes and I only got 5. So here are some of the errors that could cause our program to break. Does that make sense?
Yeah.
Yeah, this is something that's deep and complicated. Like, you really like this is getting to be really kind of like hardcore, like how the internet actually works.
Yeah.
Which is, I think this is really cool because it's an interesting. So here you go. This is the socket module. Like, I'll put this in Slack because it's interesting. So here's the socket module, and here's a couple of the errors that it has. The one we're going to also deal with a lot is socket exception socket.timeout. So this is like if we connect to somebody and we're like, you know, when we establish like the TCP connection, for example, it's like if we try to, you know, establish the connection and they're not responsive, it doesn't cause an error immediately because the network, you know, it takes time for packets to fly across the network, but you can set like a timeout where, you know, you don't want your program to just sit there waiting for your peer forever. And so this is one of the common errors we'll see quite a lot. Yeah, we're gonna understand more about this. Like in the future, what we could do. Yeah, what we could do is, you know, append them to this little thing. But yeah, let's just ignore that for now because this is a shitty program. We want to kind of get rid of this. We want to improve this. This is like a starting point. So yeah, those are just a couple of the errors that we'll see. But it's really complicated. Like, you know, it's hard. These things can fail in so many ways. Okay, that makes sense? Any more questions? How many? I only see. So we still got Gustavo. Oh, we still got 5 people. That's good. I'm always scared you guys are just going to abandon me. Okay. So this was like a little bit of. So what I'm trying to kind of go through is like we're trying to understand what our program's doing and how to like improve it. So these are just a couple. Like we got a status. Like it's just too slow. It takes 10 days. It's pathetic. So here's this little thing. Anytime you see a percentage in a Jupyter Notebook, it's loading an extension. And so this extension is in this, you know, you can read about it a little bit in this little block of text. So this little thing called line profiler. It just takes your function and just basically it measures how long your function spends on every line. You know, so if you're trying to find like what part of your function or your program is slow, a profiler like this can be really valuable because you can run your function, your program through it, and it'll say how long it's taking. So like, let's just run this. Everyone run this. So Shift Enter, run it if you can, and it'll go through this stuff. Let's just like run it so you can see it's doing stuff. Let's just run it for a couple more seconds. And then if you press I twice, you'll kill it. And you should see a little thing pop up like this, a little window. And so this is like, to me, this is like, this is magic. This is really cool that Jupyter Notebook can just do this. You just like one line, you can run your program through and it'll tell you where it's spending time. So if we look, like here's our code to the right here, def simple crawler, right? This is what we see. And over here to the left, here's the line number. Here's the number of times that line was hit. Here's how long cumulatively your program took on that line. Here's kind of the average per time it went over. And here's the percentage of total time that was spent on that line. So this is kind of the interesting column here. And if you see, almost everything's 0, right? Like if we go through our program, print packet dot from socket, the thing Alex asked about, and then the handshake. These are the only times there's our program really spends any time, you know, obviously there's a little bit of time spent on the other stuff, but like look at cumulatively, these are just taking up all the time. And so the question is, well, oh, that's interesting, you know, basically 2 lines are the entire problem with our program. So that's cool. We can get rid of everything else in our mental model of what's wrong. And so this is we're kind of back to Alex's question. It's like, well, if this is taking 93% of the time, and actually this will go up to like 99% the longer we run the program, you know, what is this? Why is this taking so long? And I mean, the first, basically the answer is, this is the thing, I'm gonna just kill this now. This is the thing that's doing sock.receive all the time. It's just spending a lot of time doing this, and we just keep doing this over and over and over until we get the message we want, which is an adder message that contains a new message. And for example, if our peer doesn't have any messages we don't know about, this could just be an infinite loop. It could run forever. And so that's kind of, we're starting to feel like this is probably the problem, is we're just calling this kind of over and over again. And most of the time, while it's waiting, your program actually isn't doing anything. Like it's not, your computer is kind of underutilized. You know, while you're sitting here like this, your program actually isn't using your CPU. Your program's like wasting resources right now, you know? And so, so basically what we want to figure out is how can we free up our CPU? How can we free up our computer processor to do other stuff while we're waiting, right? Does that make sense? So any questions about this?
No, everything seems fine.
Cool. So it's, I mean, this is a deep topic, like profiling and stuff. So this is just kind of an intro to it. And like, this is a cool tutorial up here. I'd encourage you guys to read this tutorial. And, you know, if you can go like online, there's, you know, just search like profiling Python code or something. You know, it's kind of cool to learn some little techniques for how to see what's fast and what's slow. And so here's another technique. Is like I got this little function here that will basically spit out a graph of how long things are taking. So we're just going to go, let's just do this, runs. No. So all this does is it just makes the our list of runs. It just takes the first 2, the start and the stop time, and it disregards the you don't really have to understand this terribly. Like all we're doing is we're just going to feed in a bunch of start and stop times into this function that'll give us a graph. And so if we run these 3, you'll see, what the hell? Interesting. Let me.
So just to go back on the topic that we were discussing up until a few seconds ago, basically you're telling us that we need to learn how to multi-thread, I guess, if I'm not wrong. Is that it? Is that the answer to the question of how you're?
Yeah, that's the approach we're gonna use.
All right, I see.
Okay, well this got kind of botched. Well, here, let's improvise. And so if you look on Git, so I'm kind of like messing with the notebook, but I think this one should have a better kind of a graph. Oh. Let's see. I should be able to. Okay, I'm just going to copy this. So yeah, just ignore all this crap I'm doing right now. So I'm just like putting in some data that I know works. Okay, so here, this is good. So this gives us kind of a graph of what our program is doing. And so on the right is like the loops, like the different times we've looped in our code. And on the x-axis is how many seconds they took. And so you can see basically the first two loops like are invisible. Like I don't really know what happened there. And then the third loop, it took about 15 seconds. You see, so from 350 to 4. No, that took like longer than that. That took, yeah, like 75 seconds. So that task took forever. This one took a couple minutes, right? So it's just sitting there waiting for one of these adder messages, and it's taking forever. So these two are errors. They just happened immediately. Now here's another one. This one was a little faster, and this is another one. So you can see, like, in all this time, like, if we could find a way to run all of these at the same time, our program would be cut in half, right? If we could just, you see all these over here, if we could just stack them at the beginning and run all 8 at the same time, that would speed up our program by double. Does that make sense? Because we'd be as fast as our slowest task. And so this task took about half the time. And so if we were as fast as our slowest task, we could cut it in half. And if we make it longer, we could speed it up even more. So does that make sense?
It does.
Yeah, so here's just an example. Like, this one just takes out all the failures, and this one is just the failures. You see the failures fail really quickly. The successes are the ones that are taking all our time. Is like, especially this one. Like, this one just takes forever. This is like 3 minutes. So yeah, that's kind of the statement of the problem. And so we can only communicate with one at a time. And so if we could figure out a way to commute with, and we're spending 98% of our time basically waiting for our peer to respond to us, right? And so if we could, what we want to do is find a way to do something else that's productive during that 98% of the time. And if we could cut that down to, if we could do something productive all this time, we could get at least a 50 times speed up. And that would be good. I mean, then our program would take like a couple hours, and I think we could speed it up a lot more from there. But so that's kind of the intro, and then I'm going to where's the tutorial? So let's just kind of. So this is basically the answer to our question. Actually, let's anybody have questions about this this graphing thing I just showed you?
No.
Does it make sense how, like, if we could, how only one thing is running at a time, right? And how we'd be faster if we could run them all at the same time?
Yeah, it does.
Yeah, makes sense.
Okay.
Yeah.
So that's the goal. Is like, let's run it all at the same time. Let's not spend all our time waiting. And so here's a tutorial. I'm just going to kind of go over it, and I encourage you guys to kind of like go through the tutorial later. I think it's really good. This just describes, it describes concurrent programming. So concurrent means doing more than one thing at the same time. And so there was a good talk, I forget who gave it. They're like, concurrency is walking and singing at the same time, for example. Currently our program will walk a little bit, and then it'll stop walking, and then it'll start singing, right? It's like it can't walk and sing at the same time, right? Like, it can't be doing a handshake with one peer while waiting for a version message from an adder message from the other peer. It can only do one thing at once. And so basically there's two kind of classical approaches to this, and they're called threads and processes. Like, if you go to your computer, if you have a Windows computer, and if you hit if you just hit PS space X, I don't want to share a different window, but just go to your terminal and hit PS space X and hit enter. This will just give you like a printout of all the different processes that are running on your computer right now. So I'll just give you a moment to do that. Did you guys find that?
It was PS
space X.
Yeah.
Did that work, Ivo?
It's in the command prompt, isn't it?
Yeah, yeah.
No, for some reason it tells me that it doesn't recognize the command. Can you please paste it on Swag to make sure that I'm doing the right thing?
Oh, sorry. That's wrong. Do you have a Windows computer?
Yes, I do. I have been printing the exact same command as on Swag, but for some reason it tells me that it doesn't recognize it. I don't know why.
Okay, so if it's Windows, it might not work. You have to have either a Mac or a Linux.
Oh, right. I can always, yeah, I'll open the Ubuntu.
Yeah, so that...
Okay, yeah, I see it now.
Yeah, so this is all the processes running on your computer. And so basically what multiprocessing would do is it would just create a few of these. Your program would just use a few of these. And you can kind of see it's kind of interesting. Like for me, I could see my Chrome browser has a lot of different processes. And I can see that my Spotify app has one process that is called the GPU process, which is probably for the music. And I can see another process is for the renderer, which does the UI probably. So you can see that some of these apps that run on your computer do have multi-process architectures. And I think that's pretty cool. And so the one thing, though, is these processes are kind of expensive. It's hard to spin them up and down. And you can only have a couple hundred at the same time. Your computer just runs out of power. And threads are like similar, but they're a little lighter weight. They're like a process can have multiple threads. These are just like your program can kind of execute a few things at the same time. And they're just a thing that your operating system provides you. It's like the operating system will just allow you to have this separate kind of execution environment for your code. And so they're a little bit less resource intensive. And the one thing is it's really easy to have bugs when you start to do code like this. In a previous version of this, I had a really cool demonstration of a bug, but I don't really have that anymore. So basically, like one thing that can happen is like, let's say you have two threads, right? And let's say they're both writing to the database. You can very easily have a situation where like one thread will read a value, the other thread will read the same value, or the other thread will read a value, and then they'll both like write at the same time, and they'll conflict and like destroy your data, sort of. And so there's all these, I mean, you've heard the word probably race condition. Like race conditions are what happens is you get all these, it's very easy to have bugs in your code due to race conditions. And so this will allow us to make our program faster, but it'll also be tricky because it's very easy to introduce bugs. So does that make sense, that kind of overview of these two different things?
Yep. Yeah,
It does.
Cool. So we're going to do threads.
And sorry, did you say we're using processes and threads, or one or the other?
We're just going to use threads, and there's not a good reason. Well, there is a good reason. So you can have more threads open at the same time. Like with a process, I think you can only have a couple hundred, but with threads, I think you could have a couple thousand. And so, you know, we're going to maybe want to have like 100 or so, maybe a couple hundred open at the same time. You know, because it seems like, you know, it takes about 10 or 15 seconds, 10, 20 seconds to, you know, talk to our peer and get their message on average. And so if we could be doing that with 100 different people at the same time, and there's 10,000, we'd only have to do that 100 times to get through the whole network. You know, if we had 1,000 connections at the same time, we'd only have to do it 10 times. So, you know, we could get through the whole network in like 3 minutes. So that's why we're going to do threads, is we can have more connections open at the same time. That make sense?
Yeah.
Cool. So, so yeah, you can so a cool thing, like if you run this code, and I encourage you to run it on your own computer and like try to understand what's going on. And so what this code does is like, you see how when it prints out, so the first little block is a serial. So this just is like running normal Python code, right? And then the second block is in threads, and this third block is in parallel. in with processes, right? And so all the thing is doing is that it's has a while loop that counts up to like 10 million, right? So it's just like some stupid thing that wastes your computer's resources. It just like occupies your computer for a second. And so you see there's 3 different blocks, and we want to see basically what and they have a special print function here, right? So what the print does is it says what process ID it is, what the process name is, and what the thread name is. And so usually when you're doing Python programming, these are all going to be it's just going to be the same every time. It's like the main process, the main thread, and whatever the PID of this is the process ID. This is just a number that your computer gives the process. So if we go and run this, you'll see the threaded version, or the normal version, just the good old fashioned version. Like every time it prints, it gives you, so it just runs it 4 times basically. So every time it prints, see the PID is the same, the process name is the same, and the thread name is the same. This is how Python code and code in general usually works. It's like it always runs in the same process or thread. And so if you look at this one, this is the threaded version. See, the process name is the process ID is the same. The process name is the same. But when you go over to thread name, it's different every time. It counts up to 4. So you see that it's sort of like when you run this code, all of a sudden your print statement is being executed in a different thread. It's like a different entire environment. And now if we go to the multi-process one, you'll see the process ID is the same, is different every time. So like, if you went and if you ran this code and kind of watched your PS space X output as you ran this, you'd see 4 different processes on your computer. And you see here they have different names, 1, 2, 3, 4. This is just the default numbering. And each one of them is running in the main thread of that process. So every process has multiple threads. But when you're doing that, there's no need to use both at the same time. So they just all run in their main thread. So does that kind of make sense, this output? I thought this was a really, okay, cool, Ivo. You can record it, or the recording will be up soon.
Yes, thank you, Justin. Goodbye, guys.
Yeah, bye-bye. So does this output kind of make sense, like what's going on?
Yeah. We just take for granted or assume that if they have different process IDs that they are running simultaneously?
Yeah, I mean, so they are, they are, they are. I mean, that's a tough question, like to actually, like in this example, they kind of are running simultaneously, but in order to verify they're all running it, they're all running simultaneously. That's a simple answer to the question.
Okay, cool.
It's kind of a complicated thing, but so we're not going to deal with different processes, but we are going to deal with this one, these multiple threads, right? So in our program, we're going to want thread 1, basically, to go back to the beginning of the lesson. When we spin up our program, remember we have these things, we're going to want thread 1 to go and talk to this guy, right? And we're going to want thread 2 to go talk to this guy, and thread 3 with this guy, thread 4 with this guy. Ideally, we'd have like 100 threads, and we'd have 100 IP addresses. And we just say, okay, starting gun, everyone go talk to your node. And that way we'd have a lot less time. Basically, what Python does is it jumps back and forth between the different threads and does a little work for each thread. And so it doesn't actually like execute the base level instructions at the same time. It just kind of jumps back and forth. And that's what we want. We just want, like, let's say you go and talk to this node or this guy. When it hits a point where it's waiting, we want our Python interpreter jump over to this thread and help this guy. And every time it gets to a point where it's waiting, our interpreter will jump over to these different threads and do work over there. Right? Does that kind of make sense?
Yeah. Yeah.
Cool. So that's kind of the end of the... This is the end. Yeah, oh, the other important thing is, like, look at the times. See how this one took 4 seconds? See how this one takes 1 second and 1 second? basically by adding 4 threads, they were able to speed up the process by 4 times because they could do work simultaneously. Because this function they're doing is just sleeping. It doesn't do anything. It doesn't do any intensive computation. And so sleeping is basically, what did Gustav, something about Node? Yeah, so sleeping is basically what our network programming is doing. Like when we're waiting for our peer, we're basically sleeping. We're just like sitting there doing nothing. And so we'll hopefully be able to get a similar type of speed up. And so this is basically, in Python, there's all these different ways to do it. And there are actually some newer ways that have been invented since this. And we're basically just going to do this is like the old-fashioned way, the standard way of working with, this is like the standard way of getting concurrency. It's like the old-fashioned way. And we're just going to do this for simplicity's sake. Maybe on the next version of this class, I'll do something really cool with one of the new ones, but sometimes they're a little harder to debug. And yeah, so Gustavo mentions that Node is single-threaded, so you can't do this. But the one thing that Node.js is really good at is it has this, what do you call it? Like, it has this kind of like, it has async kind of like event loop built into it. So
generators.
Huh?
It's called generators.
Yeah, generators. Yeah, so it has generators, which make it so you don't really need multiple threads. So for this type of program, Python's honestly not the best. Like probably like Go is probably the best. Or Rust or one of those. Node is also good. But we're going to use Python just because it's kind of good for everything else. So yeah, some languages have that kind of thing built in. And so if we want to just show you like, if you ever heard of async IO, this is like the new built-in thing to Python that should allow you to yeah, so this would kind of allow you to let's see if, so here's like a web crawler with this async IO. This is like a new thing, so I don't know. I don't think it's worth. Probably shouldn't read this, but you can. Python's trying to basically copy Node is what I'm trying to say. So so yeah, that's kind of where we're at. And if you read this, it's kind of cool. Like this program they have is just to like check if these websites are up, and that could be kind of what we have our Node do in the end. Oops. In the end, we might want our Node to go and see, how frequently do our peers fall asleep? Who has the best node? Like that's one of the things that BitNodes does. So yeah, I'd say like in your own time, kind of go through this. I think it's really interesting. Like this will really help you kind of expand your understanding of what programs do, because it's just like, it's so much it's different, like doing things at the same time. So yeah, that's basically the end of this class, because I wanted to kind of expose you to this idea, show you the need for it, and then in the next class, we're going to, let me just give you a little pitch for what we're going to do next time. So if you go to IBD for MVP_DB, I got to rename it, but this class actually has, you have this thing where we have these different workers, and these are basically threads. And what you do is we'll just like pass them IP addresses through a queue, basically like we were doing with the list earlier. And we have a crawler that will go and spawn these workers. It'll go, you give it a number of workers, and it will just say, okay, I'm going to go make some of these. And so when we run our program, you can run it with like crawler of 500.crawl. This will create 500 threads, each one of which knows how to go and contact nodes, and they'll just pull addresses and go and talk to them. And you can contact you can contact quite a few nodes pretty quickly with this program. So tomorrow I'll try to kind of go over this. It's sort of complicated, so I don't know how I'm going to teach it, but it's a pretty cool. So this is like a Bitcoin network crawler. So yeah, you can kind of check out this code. You should be able to just open that link and it'll open on your computer. But yeah, so that's the end of the lesson today. And tomorrow we'll kind of go over this. Sound good?
Yep.
Yeah,
Sounds
that's really cool.
Yeah,
cool.
really
Glad you liked it. I'm so always worried. It's hard to explain this shit, so I don't want to lose you guys. But yeah,
No, man, this is awesome.
Threads is hard for a beginner to just jump into threads and know what they are doing.
Yeah, I mean, it's kind of crazy for me to Alex has not done a lot of programming, so Alex, if you don't understand this stuff, there's some of it. It's totally okay because in Evo too, because yeah, this is like quite an advanced concept. But the way I look at it is like it's best to just kind of expose yourself, and you'll learn a ton by trying to wrap your head around it.
Yeah, totally.
So yeah, that's kind of the sales pitch for tomorrow. Let's kind of learn.
Can you at a high level just say what the like when you said create 500 threads, what's like how does the trade-off kind of work of what the optimal number of threads you want to create is?
That's a great question. I mean, I don't really know. Well, especially because our program, I mean, the one thing that is like there's a bunch of these levers we can slide to make our thing better. And like one of them is like the number of threads. And if you go and look at my GitHub, like the history for this file, you'll notice that I change this number all the time. This number here, like I'm always changing this because I'm trying to see if it's faster or slower. Like, so yeah, I don't really know yet. I mean, I don't have an empirical answer, but if you have too many, like, sometimes you can actually open too many files on your computer. Like by default, you only allow like 1,000 or so files, and after it's done, it'll leave some of these files open. Like a socket is a file. It's treated as a file. So like if you have too many, it'll crash unless you modify your operating system to allow more open files. So that's like on the extreme, too many sockets. There's too many files on your computer, but if it's too low, it's like you're like 4 times better than what we had here, right? So 4 times means we finish in 2.5 days, right? Like it's not hardly a victory, right? So yeah, it's like somewhere in between there. And honestly, like one of the other big levers is like, most of the slowness in our program is actually this. It's most of the slowness in our program is just continuing to loop through this over and over again, trying to get adder messages. And like sometimes, like if one of these guys hasn't given us an adder message in like, let's say 10 seconds, it would probably be better to just say like, hey, they didn't give us the adder message. They didn't tell us more addresses. Like, let's just throw them back on the end of this list and let's go to another one. Like, let's try to get through and find the people who will be responsive, and don't just wait forever until they give us something. So basically just cutting down the number of times we go through this loop is another one of these levers we'll do, because we can visit these people multiple times, right? So it'd be cool if we could go like crawl the whole network once really fast, and then like over time we'll dial it down and kind of wait longer for the sluggish nodes. Does that make sense?
Yeah.
So yeah, it's I don't know what the answer is. It's you just kind of trial and error. but and it's also like, this kind of profiling is like, if you want to write a good program that does something interesting, and like you write one and it doesn't work, like I was having a problem when I was writing this where the memory usage of my computer would go up to 150%. And it was like, well, what the hell? Like my it doesn't actually do any hard number crunching. Why is it? Well, there was some bug that was causing an infinite loop basically. And like some of the profiling I was able to find, like with this profiling thing, I was able to find like, oh, one of these was being hit like 80,000 times.
Yeah.
Instead of 35, it was like 80,000. Okay.
That's awesome.
So this is stuff I wish people would have taught me more when I was getting started.
Yeah.
Because this is how you you get some your own freedom to pursue things if you can kind of get unstuck and debug a little better.
Yeah.
Any more questions or comments, concerns?
Yeah, I had one more. So if can you scroll up for a second?
Yeah.
Like towards the top. So if you so this function of like crawling, that if we speed it up, it takes 10 days how it's currently written to get all the addresses. We can speed it up so that it takes whatever, a much shorter amount of time, but that's only for like one run through. So to make sure that your representation of all the nodes is like accurate, when you get it sped up, do you like run it once a day, or how do you, because it's a static picture, right? Like if a new node joins, you wouldn't necessarily be aware of that. So how do you stay up to date with that? You just run it every day or something?
Let me try to give a little demo here. So, okay, I'm going to try to switch screens. This may fail miserably. New share. Can you see this?
Yeah.
So this is like in our new version, we have this is like a little SQLite database, which is like, SQLite. I've been learning a lot about it recently. It's really cool. It's like a little database that is just in a file, and it's a SQL database. So it's this, SQL is structured query language. It's this, it's the standard way of kind of querying databases. And it's really, really powerful. And the cool thing is it just sits on a file on your computer. So basically, it's just sitting on a file, and it's about 1 megabyte big, and it has kind of records for like 1,000 nodes. So actually, well, I guess I just deleted it recently, but if you look, these are all the nodes I found out about from running my script. And so, I got like 7,000 nodes. And I just deleted all the start and the payload and everything. Actually, so some of the errors are still here. So let's just try this. Check error count. So I think this should work. Oh. Never mind. I guess I like deleted. Sometimes I delete a bunch of stuff from it, so it's not going to work. But so this will, like, the point is, like, you can, every time you run this, you just have this little database file, and you can fill it out more as you go. And so the idea is, like, once you know of these things, like over time, you don't have to ask people for their adders as much, and you could have two ways of running it. One could just be like, you just run through all the peers you know about and really quick, like, see if they've changed their version messages. And you could run through that in like probably a couple minutes, probably like a minute. And so so you could run that every 5 minutes actually. So like what you'd probably want to do is you'd probably want to have two of them running. Like one of them is the slow crawler who doesn't even maybe care about the versions. It just tries to get adders, right? And this is really slow because it's just like, it's on all these different weird parts of the network, and it's trying to like go, it's like a truffle hound, it's looking for truffles. And and then the fast one, maybe you have it on a cron job, like every 5 minutes it goes and sees what happens. And I bet that's how this Bitnode site works. So yeah, that's kind of what we're going to go for, is like one of them will run frequently, one of them will run slowly and just try to like find new shit. And I mean, the other thing that would be really cool is to build like a topology, like a literal topology, like, like for every given, you could throw it into like a graph database and say like for every given IP address, who told us about this? Like, which IP addresses know about each other? And then maybe like, you know, you get some more stuff like, you know, their geographic location and say like, okay, well, what are the patterns here for who knows who, you know, like that. I think that would be kind of interesting. I don't know what the hell you do with it.
It would, yeah, it's like chain analysis, but for the node network.
Yeah, exactly. Yeah, I mean, but this is how, you know, when some like government agency tries to track down, you know, someone who tried to pay for like an execution or drugs or something with Bitcoin, this is kind of what they do when they're trying to figure out what their IP address is. You know, like if they got the coins from mining, so you can't, you know, there was no on-ramp, they could go find who the person is, then they'll try to, you know, trace some address back to an IP and then find the IP physically, you know. And so similar kind of techniques to this would be used to like monitor the entire network, right? But they do it with many different nodes. They'd want nodes all over the world, so then they could, you know, given a certain transaction, they could kind of pinpoint where it was originated from. So there's a really cool talk about this at the Building on Bitcoin conference about, what was it? It was called dandelion routing. So it's just like a way to it's like against this type of thing.
I went to the BitDevs meetup in New York this past week, and they talked about dandelion routing, how basically you can like kind of like distance yourself from, like, you kind of like delay the propagation of the transaction for like 2 to 3 different nodes until it like poofs out like a dandelion.
Exactly. Yep. So that would just make it much harder for them to pinpoint where it came from. And so, yeah, this gives you an idea of how, you know, without dandelion routing, what you could do to spy on somebody, try to figure out their actual IP from, you know, given a Bitcoin address, figure out what their IP is. You know, you'd wait for someone with that Bitcoin address to broadcast a transaction, and then you'd try to, you know, use all your nodes in the network in your network topology to say, okay, it came from one of these 10 or something, you know. And then you try to connect to those. You try to connect to those and wait for the next thing to be broadcasted, and then maybe you can pinpoint it.
So this list is, as we said, it's not only full nodes IP addresses, it's everyone that has interacted with the network in any way.
It could be. I mean, if you had someone like in the extreme, like to get a Bitcoin transaction onto the network, like you have to broadcast it on a connection that has done the version handshake. You know, to get it out there, you have to do the version handshake once. But like, you know, if you wanted to be super paranoid, right? Like you could go and go to a different country, plug your computer in, run a raw script that does the version handshake, broadcast a transaction, pull the plug, burn the computer and leave the country, you know, like, so you wouldn't actually be a full node if you did that. But like, you know, conceivably, if, you know, somebody asked the peer for their list of peers, they would tell you about this paranoid guy, because it's like, that's just how the software works. It just keeps track of who it's talked to. So that kind of, I don't know, it's kind of a long answer to the question. Any other observations? All right, cool. That sounds like it's probably about it.
Yeah. Sorry, one last thing. So related to that, so when if I like I'm not running a node, but if I'm like sending Bitcoin, would my IP ever be in on this list or no?
I mean, it depends how, like by sending Bitcoin, like let's just assume you mean like you're sending it with Bitcoin QT, right? Like the wallet that's built into Bitcoin Core. Like in that case, let's, because I'm not going to ask you how you actually send Bitcoin, because it's is recorded. So like let's just assume that you're saying Bitcoin QT. Like Bitcoin QT, your IP would, unless you do something, unless you connect over Tor or something, it would be out there, because Bitcoin QT just connects directly to, it goes and finds known peers through DNS seeds and just connects to them with raw, just exactly like what we do. It uses the same mechanics to go and talk to them. So yeah, you would need to, your IP would be out there.
Interesting. Okay, cool.
Yeah. Any more?
I guess that kind of relates to why some people think Lightning is actually, it will actually be pretty good for privacy, right? Because you're theoretically obfuscating.
Yeah,
like
I
that
don't know.
wouldn't necessarily be as.
I honestly haven't learned much about Lightning yet. I'm actually hosting a hack day on Sunday. If any of you want to come to Austin for a 6-hour hackathon. No, I haven't learned much about. I don't really know how Lightning works yet. I'm trying to understand how Bitcoin works more, and then get more into Lightning. But I've heard the same thing. Yeah, there's another interesting building on Bitcoin thing called pheromone routing, which is like a anonymity thing for Lightning routing too, which is PHEROMONE or something. That's another interesting thing. But yeah, I've heard that. I don't really know. Oh yeah, I mean, yeah, it's just because I mean, like a big, it's kind of like CoinJoin, right? Where you have, to make a settlement on Lightning, you have all these different parties that need to like settle against each other. So you don't really know where the coins came from.
Yeah.
I don't know. Sounds cool.
Definitely.
Alrighty. Well, that's 2 hours. So let's 1 hour, 45 minutes. So let's come back tomorrow again, same time, noon, and I'll try to actually walk you through this more complicated crawler that still doesn't like totally work. I'm still kind of like ironing out but it's pretty cool. Like I wrote there's this little like report that you can kind of watch the status of it. So it's like you can watch your crawler crawl. It's pretty cool. So I'll show you how all this works tomorrow.
Awesome.
Alrighty.
Thank you so much. This is great.
See you guys tomorrow.
Thanks, Justin.
Yeah.
Bye, guys.
Bye-bye.
Bye.